Now that we've had a look at artificial intelligence in general, I want to start getting down into a little bit more technical detail about specific technologies that fall under the heading of artificial intelligence. In particular, so this week we're taking a look at expert systems, which are also known as knowledge-based systems. There were a few things that fell under the heading of AI that came previous to this. But this was really when artificial intelligence found its way into the business world. The first commercially successful implementation of artificial intelligence was in the form of these expert systems. And depending on who you ask, these expert systems might be, something of a relic of a bygone era. Um, I don't think this is the case. And I'll tell you why in just a minute. But so what do we mean by an expert system? So these were an attempt to just represent the knowledge and experience of a typical expert. So whether in medical field or engineering or even counseling or technology. Um, the idea is that there are experts who have something in their head in the form of knowledge, and they use this knowledge to make inferential conclusions, to combine the knowledge to bring in new facts and then come to some kind of decision. And so the question was, well, can we simulate this with a computer? This doctor, let's say they're a physician, they have some expertise that's in their head. Is there a way to just build a system that will do the same thing? And so this is really what expert systems were about. So, to this point about, yes, these were the first ones. Some of these were developed in the 1950s. The 70s and 80s really saw a boom for expert systems, and they are still around. I'll show you a couple of scholarly journals that I myself uh, read and edit and occasionally publish in. There's a journal called Expert Systems with Applications. Here's an article that I had a few years ago in there. And you can see that there's still an active area of research. They've got some they're still making developments that are useful commercially here. Here's an article on aspect extraction for opinion mining with a deep convolutional neural network. Hopefully that'll seem a little less obscure in a few weeks. A belief propagation based method for task allocation in open and dynamic cloud environment. Sequential three-way decision and granulation for cost-sensitive face recognition. Okay, so expert systems are still being researched, and various complexities are still being worked out by academics. There's also a journal called Knowledge-Based Systems, which I do reviewing for. I've never actually published in here, but um, they also publish similar articles. Here's something about human activity recognition with smartphone sensors using deep learning neural networks, um, collaborative filtering and deep learning based recommendation system for cold start items. Cold start, in terms of recommender systems, has to do with an item that doesn't have anybody who has liked it or consumed it. How do you draw any conclusions about who would like it? So it's recommender systems. They're publishing on that, knowledge-based systems. Um, but one of the reasons why folks say that expert systems are not really used is because of a kind of lack of trust that came about. The idea that a machine can incorporate not only the explicit knowledge but also the experience and the wisdom of a human expert um, seem to be a little bit far-fetched. And so some people have gone this way. This other journal that I publish in occasionally is not necessarily having an expert system that draws a conclusion, but rather a system that gathers and presents evidence in a way that then enables the actual human decision maker to incorporate as much of that into their decision as possible. So, here the intuitive intelligence and the experience is still being put on the human is doing it, but the role of the machine is to do the things that the human can't, and collect a lot of data and integrate it and present it. Um, so these are two very different kinds of systems: expert systems and decision support systems. Okay, so this question that underlies the development of these, and I hope that you've been enjoying the reading about various expert systems. Um, the the question is, can a computer draw inferences as intelligently as an expert? And if so, how do we store and use that expertise? Well, let's take an example here. This is a you know sometimes doctors just have to differentiate between a couple of similar kinds of illnesses. And here's a very simple chart that differentiates a cold and a flu. So it creates this chart here where the features are these various symptoms, and then it shows you how frequently the nature of that symptom in a cold versus a flu. So you might say, okay, well, here is a small instance of expertise. We can very easily put this into some kind of expert system that does something like this, where we have two variables. We have a cold variable and a flu variable, and we just check each of these things. Okay, well, if the onset is gradual, um, uh, then this should be flu. Flu is equal to flu plus 1. Okay, so the idea is that as we go through each of these symptoms, we accumulate evidence for one or the other. So if the onset is gradual, then we increment flu. Otherwise, we increment cold. And so, like if there's a fever, then we increment flu. Otherwise, we increment the cold. So we go through each of these conditions, and at the end, we just see, okay, which of the two has accumulated the most evidence. And so if fever is greater than cold, print, it's probably the flu. Okay, so this is kind of a bit of a brainless example, but you can imagine where it's not too hard to extrapolate from here and to think about, well, can we make a system that not only differentiates between these two, but maybe 100? And because the computer can do things pretty quickly and store things, evaluate statements pretty quickly, it can scale very well. So this is the mission of an expert system, is finding an expert whose insight you rely on, and then really codifying what exactly are they doing. Okay, so you've probably seen this one mentioned in your some of the readings. This is exactly what the Mycin medical diagnostic system did. They were developing this at Stanford, I think, in the 1970s. And this was although there were 600 rules, they had to so by the way, the rules really are just these statements, these if-then statements. Okay, so one way to set a rule is just, if it's this, then this. Okay, so that can be just called a rule. Okay, so these are rule-based expert systems. So in the case of Mycin, they had 600 rules to diagnose the presence of certain bacteria and then recommend antibiotics. Okay, so these were just if-then statements that looked for certain markers and then made recommendations on the basis of those. Now, in our example here, all we did was just kind of add up numbers, which is not really the right way, because some of these are going to have more of an impact on the final decision than others. But if you think of each of these as a piece of evidence, then you can combine it in sophisticated ways. And in the case of Mycin, they use something called Bayesian Inference, where if you know Bayes' rule, you start off with a prior probability of certain conclusions, and then you incorporate each piece of evidence. Each piece of evidence updates, and then you wind up with a posterior probability distribution. So that's what they did for Mycin. But Mycin was not actually ever used. They had ethical concerns about the role of computer-based decision making in medicine. But it did do something that was very important and influential, which was that it inspired the creation of development environments for others who did want to make expert systems that actually were put to use. So they came up with a framework for how exactly you go about this challenge of knowledge engineering and how exactly you structure a system like this. And they actually built tools so that other people could use these. And I'm going to show you a couple of those in just a minute. Um, okay, so the general design of an expert system here is the big part is right here in the creation of the knowledge base. So you have some kind of expert whose expertise you want to automate, and you have somebody called the knowledge engineers, basically translating the expertise into if-then statements. And these become the knowledge base. Now, there's other ways of representing knowledge besides if-then statements, but that it turns out that a great deal of experience can be codified as if-then statements. So you have this knowledge base, and so this process of going from the expert to the knowledge engineer and into the knowledge base, this is the real bottleneck for these things. The rest of this is actually fairly straightforward, but if a bank is going to implement an expert system on whether to give loans, then the real time consuming part of the construction of such a system is going to be in the knowledge engineering part of it. Okay, so here are the other pieces. When a new case arises, they're going to interact with the user interface, and they are going to they could update the knowledge base, but really they wanted to invoke the inference mechanism. Okay, so they will input some facts about the case at hand. The inference mechanism will look at the facts, consult the knowledge base, and then see what kinds of output it should create on the basis of that knowledge base. There's also in these systems an explanation mechanism, and I'll show you an example of one of those in a second too. So if, for example, a user is trying to decide whether to grant a mortgage, and they use the expert system for that, they're not only going to get an up and down, but they're also going to get an explanation for how exactly the expert system came to that conclusion. Okay. All right. So how do we go about what were these things actually implemented in? And I'm going to show you a couple of these. So there was a when they first started undertaking this computer to evaluate logical statements challenge, there was a language called Prolog, which I think was short for processing logic or something like that, but it's a logic-based language, which makes it easy to anytime a language is designed, it's usually designed for a particular purpose. So in the case of Prolog, it was designed to make it easy to make deductions on the basis of claims. Okay, let's see. Well, let's take a look at that. I want to show you a little bit of Prolog because it starts to show you how you can make a computer come to some deductive conclusions. Okay, so the classic example that's often used, like in logic classes or philosophy classes, is this, what's called a syllogism, where you have a statement like all men are mortal, Socrates is a man, and the conclusion is therefore Socrates is mortal. Okay, so this is this last statement is a conclusion, which is a deduction from these premises that came before. So we have all men are mortal. All right, this is the so-called major premise, which makes a claim, some kind of claim about some kind of universal condition. Then we have the minor premise, which points to a specific instance, and then you draw the conclusion from, by deductively moving from the general case to the specific case, and then you can draw this conclusion. Okay, so this is a form of thinking, right? Deduction is in something that the computer can do. So let's look at this Prolog language that was designed for this. I'm using something called SWI Prolog. I've never actually professionally used Prolog, but it is fun to play with, and I'll show you I'll show you why. I put in this what this what Prolog can, how you would express this particular syllogism in Prolog. So what this is stating, so this is the major premise right here, and what this is, um, the way this works is this mortal is the way you can read this is if uh, somebody is mortal if they are human. Okay, so if you can go backwards, you say, well, being human implies being mortal. And this x as a parameter here is just saying, okay, whatever is human is mortal. So uh, mortal is implied by being human. Okay, so we have, this is one statement. Okay, this is one clause. Now we make another. This will be how we code in Prolog our minor premise, that is that Socrates is human. So we have our it looks like a function call, but what we're doing is we're saying that Socrates is human. So whatever we put in parentheses at here is the parameter for this particular logical statement. Okay, so so we've got our major premise and we've got our minor premise, and now we'll go ahead and run this. We'll go ahead and inform the Prolog interpreter about these truths that are part of the universe of truth, and we'll go ahead and ask it a question. So let's see. I have to pull this logic. Okay, so I've pulled these two clauses. It says, okay, I've got two clauses, and I'm now informed, and you can ask me a question pertaining to that. We could call it, a very, very rudimentary knowledge base. Okay, so now the question that we would have, of course, is we want to know, is Socrates mortal then? So we've stated that he's human, and we've stated that human is mortal. Now the conclusion would be, is Socrates mortal? And it tells us, yes, that's true. And we can do another case, and is Jim mortal? It says no, Jim is not mortal. We don't have any evidence of that. Okay, so we can do a little bit more. This is a very simple deductive case, but there's more that we can add. We can another thing that's mortal is an animal, right? So we could say, okay, if something is an animal, okay, okay, I need a period there. Okay, so if something is an animal, they're mortal, and we can also, okay, let's do a chain of reasoning here. So a human, being human implies that you are an animal. So we can say animal X, okay, being an animal is implied by being human. Okay, so we've got a few more clauses to bring in here. So let's go ahead and, so-called consult in the, okay, discontinuous, let's see, mortal X, animal by human, current predicate. Okay, well, we've got, let's see if this will work. So let's see, now we want to know, okay, well, is Socrates an animal then? Okay, and it is true. Okay, why is he an animal? Well, because we've stated that Socrates is human, and we've stated that human is an animal, and so we don't actually need this piece. So if we can now do this chain of deduction where we say, well, we could say that Socrates is human, and a human is an animal, and an animal is mortal. So we actually don't even need this clause up here anymore. Okay, so these are kind of fun examples, but you can see a case where a logical problem can be solved in here. If you can very simply make logical statements, things that have to be true, things that imply other truths, and then at the end you can just say, okay, well, is it true that this? And so sometimes these complicated cases that a human can't possibly reason their way to the right conclusion, a computer can combine them in a way that a human can't necessarily. Okay, so Prolog, I don't know if it's used very much commercially anymore, but it was one of these one of these early inspirations for how exactly you go about building an expert system. Well, Prolog is a very likely candidate. Um, Another one that was under consideration is kind of considered the big language for artificial intelligence programming is this one called Lisp, which is short for list processing. Um, this is one of these more bizarre. I mean, I learned a dialect of Lisp called Common Lisp. There's also one called Scheme, but this language has only one punctuation available, and that is the parentheses. And so, you make, just like any programming language, you have uh, keywords and functions and variables, and um, but the only syntax that's available to you are various nested parentheses, and so you wind up with stuff that looks like this, and then you wind up having trouble with your nesting, and you often end with several closed parens like this. So this is what Lisp would look like. So Lisp was the inspiration for for the expert system shells. Now you can make an expert system in what's called a general purpose language, so something like C, C++, Java, of course Python, JavaScript, Objective-C. So these languages that can do anything, they can also do coding for an expert system. It's just that they're not specially made for that, so often it's going to be more vociferous, more wordy. It takes more lines of code to make those. Um, so, but with an expert system shell, and these were the things that Mycin inspired and helped to organize. It gives you a nice convenient package for you to just explicitly state some rules and draw conclusions on the basis of those rules. Okay, so you see, it's like the Prolog system, but it brings in specifically this idea of a knowledge base, and then inference, and then the application of those rules to come to a conclusion. Okay, so there are a couple of expert system shells, and I'm going to show you one in just a second. We'll actually play with it. So you buy an expert system shell, and with a fairly straightforward syntax, you can just start stating these if-then rules. Okay, the most popular, the one that's kind of got the most traction as far as history and developing its reputation is CLIPS, which is the C language integrated production system. So a rule, an if-then rule, is also called a production. So that's why they call it a production system. And the one that I'm going to show you is JESS, the Java Expert System Shell. Okay, so as you can see, Lisp has a syntax like this, and CLIPS got its inspiration from there and looks like this. Okay, and I'm going to show you what JESS looks like. Okay, so I've made a very simple expert system here that takes a couple of facts and decides whether to grant a student an extension. Okay, so this is replacing the expertise of the teacher with regard to whether it's a good idea to allow a student to turn in an assignment late. Okay, so you create these facts in here by making assertions. Okay, so I'm going to start off by just saying, from the very beginning, it's extension allowed is false. good student is false and good excuse is false. Okay, so this is the default condition. Okay, and so what I have to do is uh, come up with a set of rules using this def rule syntax. So you see how it's got that Lisp-like syntax with opening and closing parens here. But I'm just going to show you a couple of these rules. So I've got some rules here. This is a rule. You use the syntax def rule. So this is just text. You just write this in a text editor, and then you run the JESS interpreter, and it will give you your output. Now I have it kind of simplified here because I've got it inside of my my integrated development environment. But you see I've got a rule here that says, okay, if the GPA is above 2.8, they're a good student. Okay, so this is the comment, and this is actually where I'm putting in the code. Okay, so this just says, okay, if the student is, oh, actually I added more more rules here. So if the student has a GPA of greater than 2.8 and they are, above year 3, then, assert the fact that they're a good student. Okay, so a rule allows us to assert certain facts. Okay, so there's another rule here that's called check the excuse. Okay, so if the topic of the excuse has to do with family. Now, whether this is a great rule, you have to rely on expertise, but as far as the system is concerned, any excuse that has to do with family is going to be a good excuse. Okay, and then finally, the rule. Here's another rule that combines other rules. Uh, if if it's a good student and a good excuse, allow the extension. Okay, so both of those things have to be true. It has to be a good student and a good excuse. Then you assert this other fact that the extension is allowed. Okay, so the knowledge base then that this is building is really just a collection of rules. Okay, and you can see how in the comments, these are expressed as if-then statements, but the syntax here is more just assert. Okay, so and you use this thing here. Okay, so it's got this special made syntax to make it a little bit more terse. To make the purpose of the language is to express rules, so it has shortcuts for expressing these rules. Okay, so up here at the top, I'm just these are just creating records into which you can put some slots. So like I'm making a student that's going to have a name and a GPA and a year, and then I've got an excuse template. You can think of this as an object or a record, and the slot here of interest is going to be the topic. Okay, so here is where I'm entering the facts as they are according to the user interface. So you can think of these kind of properties being entered into like a form or something. But in this case, I'm just asserting them directly in the code. Okay, so I've got a student here named John Smith, GPA 2.9, year 4, and has completed 2 assignments. Okay, and I've asserted that the excuse is on the topic of family. Okay, so now I just have to run this and watch the facts. Okay, so let me make sure I'm running the right thing here. Okay, so I've got here these conclusions. Okay, so it has come to these conclusions down here. It says, okay, well, we have a good excuse, we have a good student, and the final deduction is that the extension should be allowed. Okay, so if on the other hand, if I'm putting in the student actually only has like a 1.9, then I run it again. Okay, so now the only thing that is true, the only statement that's true is that it's a good excuse. Okay, so on the other hand, if the student is good, but the topic is overslept. Okay, so now I have a good student, but not a good excuse, and so I no longer have that final rule, which is to allow the to allow the extension. Okay, so we'll go back to this, and it's okay. So now we've got good excuse, good student, and so the extension is allowed. Okay, so this is the JESS. So this is the Java Expert System Shell. This is one of these expert system shells that allow you to very quickly, once you learn the syntax, just put together all of your rules, what kind of facts imply other conclusions, and you can just run it without too much fuss. Okay, so Clips has a very similar syntax. If you look at this slide, so this is what Clips looks like, and you can kind of see that it has the same idea of defining a template, and where you put some slots, and then you define some facts and def rule. In fact, that was the same as JESS, def rule. Yeah, so really similar. Okay, so one way then that you can go about creating an expert system is to just use one of these expert system shells. Now, Java expert system shell, neither of these is terribly expensive. Whether they're in the end easier to use than a general purpose language is a question. I personally find it easier to write more complicated and more readable code in Python. So so we looked at how to do it in JESS, and so can we just say, what about Python? What about a general purpose language? And yeah, absolutely. I mean, all it is just if then statements, right? So we could just start it off in Python, and let's go back to like an example like this one, right, where we have we're going to build an expert system for deciding between a cold and a flu, and we can just have our cold equals 0, flu equals 0, and let's say so. Then we can just do if onset equals gradual, and we'd have to put in the onset. Okay, if onset equals gradual, and then we don't use an then in Python, we use a colon. So if the onset is gradual, then we do cold, we increment the cold, else we increment flu. Okay, and then in the end, we could just do if cold is greater than flu, print cold, else, colon, else print flu. Okay, and now here we have our expert system, and we run it, and let's see, did we get anything? Yeah, it says it's flu. Okay, how do we get that? Well, onset was sudden. Okay, so that one little piece of evidence that we coded in there happened to be for the flu. Okay. All right. Now, I'm gonna put up this code on D2L, and we can try to see if we can get it working. But I made a similar sort of expert system in Python to encode these same rules about giving an extension. So I showed these in the last video, but I've got the interface here, and I've got the knowledge base here, and the inference engine here. Now, remember that the parts, in addition to having the user interface and the knowledge base in the inference mechanism, it's also advisable to have an explanation mechanism. So why did you come to the conclusion that you did? And so that's something that's done here. In this case, I have it embedded within the inference engine, where as I evaluate each of these conditions, I not only return what the decision is, that is, okay, it's true, I decided to go ahead and give that extension, but then it also provides the explanation here if you want to use it. So the students meets the criteria for being a good student. Okay, in this case, the decision was to grant the extension, but the explanation, the student has a good excuse and could use a break. So each of these conditions is slightly different, but it does go ahead and provide the explanation for why it does that. Okay, so this is a little bit of a step above, but you can imagine something like this where uh, this is for a typical developer, this is a couple of hours of work. Um, um, so you can imagine with the team, a well-designed set of knowledge can actually build something that comes to some. Okay, so that's mostly what I wanted to show you. Just we'll do a little bit more. We'll maybe in class we can, in addition to discussing expert systems, try our hand. Maybe I can help you get um, Python up and working if you haven't already. But I'm going to send an email about this, but one thing I think that we should do to kick off our discussion on Wednesday, rather than do the usual thing where we discuss the readings, one of your reading assignments contains a very nice list of some expert systems that were put into actually, built and put into commercial use. It's quite an extensive list, and I think what I'm going to request is that everybody select one of these, do a little bit of research on how it works and what kinds of rules it used, and whether it was successful and what its fate was if it was decommissioned or whatever. I think it'd be really interesting to look at some examples of these and how well they worked, because a lot of the other stuff that was discussed in the readings was really more about the general technical side, which I hope I've addressed sufficiently here. Okay, all right. So good luck with the remainder of the reading, and I'll see you all on Wednesday.